Hi, my name is Tunjira Susan, and I'm working with Chugun Sulaiman, and I'll be taking you through our project, which is personality distillation for electrogastrogram signal processing to predict diabetes. And the keywords we've used mostly in this project are diabetes prediction, electrogastrograms, feature extraction, signal processing, genetic algorithm, feature selection, machine learning, denoising, and sparse knowledge distillation. And first of all, I'm going to start with a background and introduction. We are dealing with diabetes diagnosis, which is the early detection of diabetes, and it is critical for better management. Current methods are invasive and time consuming, and what we are trying to come up with is the non-invasive methods, whereby you're going to choose the EGG signals, electrogastrography recordings of the stomach electrical activity reflecting the gastrointestinal and metabolic health. And still, we are dealing with machine learning, and we're going to choose advanced techniques like sparse knowledge distillation, which I'm going to be using as the case SKD, and it can help extract meaningful patterns from complex data. And our main objective for this project is that to investigate the EGG signals and to investigate using the EGG signals and sparse knowledge distillation to predict diabetes by analyzing gastric motility in the healthy individuals. We are mainly focusing on the identifying patterns in the fasting people and and the post-prandial states, which is like after consuming a standardized meal. And in this case, we are using the oatmeal project, and our goal is to develop a non-invasive real-time predictive tool for early detection of diabetes. And our literature review, we have diabetes prediction, which is early detection of type 2 diabetes through health parameters and biomarkers, which is so crucial. And then we have electrogastrograms, non-invasive recordings of the stomach, electrical activity altered EGG patterns and are associated with diabetes, making them variable for diagnosing metabolic disorders. And next we have feature extraction, which is converts the raw EGG data to measurable features for analysis. And we also have signal processing techniques. You're going to use techniques like empirical mode decomposition, which is the EMD. I'm going to be using EMD, and filtering that helps to enhance the EGG signal quality, removing noise and artifacts for reliable analysis. And we also have genetic algorithm for feature selection, which helps optimize the feature selection by identifying the most relevant features for the EGG signals, improving the model performance and reducing complexity. And we also have machine learning. In this, we're going to be using different machine learning algorithms, such as like support vector machines and neural networks, which are trained on the extracted features from the EGG signals to like predict diabetes. And it will help us distinguish from the healthy and the diabetic individuals. And still, we are going to imply denoising because still, like I said, EMD and wavelet transforms removal noise from EGG signals, ensuring accurate feature extraction and improving the model accuracy. And like I said, sparse knowledge distillation, and this like helps transform knowledge from a complex model to a simpler one. Here, it reduces the computational demands and it helps us maintain the prediction accuracy, making it suitable for real-time and non-invasive monitoring. And our problem statement, we're mainly focusing on the computation problem statement, which is like the current diagnostic methods are invasive. This means they include blood tests and like other methods. And the main limitation for this is you continuously it cannot continuously monitor psychological changes in real time. When you want to implement it in real time, it doesn't give accurate values. And then we have technical challenges while using the EGG signals, like the noise level components that are present in the EGG signals, and they require robust processing. And next we have high dimensional data. Feature extraction from the EGG signals is often like high dimension. This means it will require dimensionality reduction to isolate informative descriptors. And this will take more computation time because we have to like deal with the already extracted features from the EGG signals, and then we have to reduce the dimensionality. And what are some of the research questions and objectives? The research questions we are dealing with: how can electrogastrogram signals be utilized to predict diabetes? Those are like the research questions we had to ask ourselves, and like maybe people that we expect like people to like be with. Like we had to figure out like how electrogastrogram signals can be utilized to predict the type 2 diabetes, then the key features we are going to consider, and that is going to help us differentiate.
Yes, hello, good evening. I'm going to continue from where my colleague has left off. So I'm going to take you through what the methodology we started that we are able to acquire what the steps were EGG signal acquisition because we have to use the signals actually. So we have to attain them from the we have to attain them from the participants. Then we perform pre-processing and then we decompose them into something that we can actually use or feed the models to train on them. Then filter the EGG signals and remove so this is the feature extraction. Filter the EGG signals by feature extracting. So this is extracting more features or features to help us furthermore understand the data set and then find ways of implementing it to be able to predict to train the models on that data set. Feature selection as we did that. Then classification of whether a person is either diabetic or not. Yeah. So the next on the other page, we have some visualization where I told you we actually pick we actually pick few features. I mean, we use few features, few important features, dominant features from 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 the patient. This is raw data. So the data has to be worked on and maybe attain other features that will help us further understand the data set so we can use that to predict. So the most important features for this case, we have the total power and spectral amplitude. And if you see this graph, the feature importance graph is showing that the more important and least important in the data set. And if there is none, for example, you have some features that can miss it for the data. You know when someone is hungry. Okay, when someone has not eaten and not been eaten, there is there is there is some there is some frequencies that will be in the stomach when someone is eaten and when they're not. So this is why this part is blank. So that makes other parts easier to explain. The KDE plates distinction between the best of the people that are basic and the people that are not. Same there is this one, the distribution of the data set. Remember, each person was taken samples twice. So before they had eaten and before they had not. So this distribution is showing that is where they're eaten because they are 2020, each person has taken twice because they are 20 making it 40 empty. So this also the heat map also makes further more clarification on the more important features as the already are the most important, which is the entropy and the total power. So the 3D dimension, this shows the mean deviation and standard deviation all at once. So you can see the variation of all of them at once. So this one shows the how this one shows the outliers depending on categories, the peak, all the features almost, yeah. So it will show you the distribution of the participants, the data set. So we need to talk about the output of the models. I mean, the performance of the models, how they performed, why, how we came up to choose which model is best, which is new, and why we chose to take on the naive bias as our best model, yet it wasn't the best in somewhat, in some other. So we performed sparse knowledge distillation, sparse distillation, and sparse learning, knowledge distillation, and sparse knowledge distillation. So we performed all the three, and we got results of all our models under all circumstances. Remember, some models can be sparse distilled, but some are not doing it. So we got performances in all those circumstances, and we noticed actually that this information, I mean the models, depending on the data we had data that had less noise. So we try, remember we had to denoise. We denoised a little bit. We denoised in the first place, and then the data was, I mean the models were not, there was over there was overfitting. The original data set had overfitting. Even the denoise, I mean the denoise data set had overfitting. So when the other one we added noise to the information, so we train the models to more noisy data so that it can make more predictions under circumstances of being tricked to predict right yet. So that's what we did. We got all the outputs. This first table is for the original data set. This was it. Actually, no. Yeah, this was it. Then this was at this second table, it was at noise level of 0.01 because we want to be in different levels of noise so that we can, can make the model more robust and we see which one is consistent and good. And that's where the naive base won in this race for which is the best model with all the others. So this is where it won because it was consistently good, averagely good, but in all situations. So it didn't alter the results didn't alter a lot. Like for example, we had another option of decision tree, but for it used to change. So this is for above. So I'm going to cut it short because the time has run out. This is for the original. This is for 0.1. So at 0.01, so there was not much change. In the next one, this is at 0.05. This is where the change came. This is where the random decision tree lost because it changed a lot. Yeah, and this is the other models. Then you have the configuration matrix of the bias names since it was the best. So this shows at the beginning it was so overfitted, it predicted everything so right for all circumstances. Then when we introduced some noise, then it went to the the performance reduced a little bit, but not so much, but it was still averagely good under all circumstances. So feature works we intend to include diabetes. Diabetes is split into two, so we want to be able to split and be specific on which type of diabetes. Then we need to work on larger data sets so that we can add more features. Then feature engineering, we need to go into deep learning so that the models are more robust. Real-time monitoring, we need to be able to monitor someone's diabetes status at any point, not after having the electrodes put on the stomach, which is more, it is close to the additional form. So we want to make it better than personalized AI models so that they are able to track someone's health at all times. Limitations, data constraints, it is hard to train these signals for training models. It is expensive to have the equipment. Then noise artifacts, sometimes the noise distorts a lot the what detection. Generally, the model performance varies when they apply to larger and more diverse populations. So conclusion, the study was about EGG of the 20, EGG extraction of the 20 people, but for this case, they were healthy and we tried to put some unhealthy individuals. So yeah, that's why it was not hitting. But when you added some healthy one, I mean unhealthy, you added noise and all that to try to train a model. So the significant outcomes, the introduction of noise improved the performance of the models in some way. Um, and then we saw the most robust in all the conditions. The use of personal identification are generalized, while while the reduction of computational complexity reduced the computational complexity. So yeah, I'm going to leave it at that due to time, and thank you very much. Uh,